So we start the second part of the battery cycle simulation. That's where we left off in our first video. So please, if you haven't watched the first part, kindly check out the video in the description below. So we wanted to actually figure out what to input at the equilibrium potential and the temperature derivative of equilibrium. So these values, wanted to figure out what we're going to do about that. That's what. And also, I remember we finished with the drawing the geometry, and also we also finished the physics aspect where we added our porous electrode separator, and also we went there to add the negative and positive electrode selection. Then we also added the electric ground and the electrode current, and finally we were able to mesh. So we move to, there's one important thing I'd like us to do before that's at the porous electrode and the particle intercalation. There's something I want us to highlight over. So when you move to porous electrode particle intercalation, you have to go to, we have to check the particle discretization, and you want to select fast assembly. In there, and also under the porous electrode reaction, where we have the reference exchange current density, we want to text that field. We want to type the reference. We want to type that as the reference the negative. Good. Same for porous electrode 2. Under particle intercalation, the fast assembly, and once again under porous electrode reaction, this will be for the positive. So we move to the steady and the time dependent. We want to change the times range from 0, step of 1 to step of 1 to which is 100. And let's look at the default solver. So in the default solver, I want to select the steps. I think we have to go to the time dependent solver, and under the time dependent solver, Under the time dependence solver, you go to the time stepping. So we have steps taken by the solver, which we have changed to intermediate. Let's select the nonlinear controller. And can go back to minimize this part. Then I think we compute to see. Okay, so I think we have to define the particle intercalation one. So the operational SOCs, as I said, we have to look for the particle intercalation column and check that the particle material is selected for domain. It should be selected from the material. So under material, want this to be material length 3. Length 2, material length 2, length 2. And also want the particle mean center surface, the mean center to surface distance. I want to reduce it to 2. So now that we've ensured that this side, the omission has been rectified, we have to also check for porous electrode 2 particle intercalation to see if we do not omit that side. As you can see in here, we did omit this side, so we have to select the particle material, and it's going to be material length 3. It's going to be for the positive. And same, we want the mean center to surface distance to do this. So we'll be able to pick up this, the SOC and everything. So now that we've been able to define the SOC marks, then we can compute to see. Okay, so undefined material property required by porous electrode reaction 1. Identified property. So we move to porous electrode reaction 1. So the equilibrium potential material should give us the equilibrium potential. So that will give us the equilibrium potential. Let's see here. And I want us to also check, maybe we did an omission for pros through the reaction and the second electrode, the first electrode. So I think we also did an omission over here. As you can see, we rectified. So you can realize that after we selected the equilibrium potential from the material, when we come back to the material, realize that everything has been checked now. So everything is now defined now. So it was the reason why we had some part not defined was we omitted the equilibrium potential for the material for porous electrode reaction 1 and porous electrode 2 and for porous electrode 1. So now that we defined the equilibrium potential, we have actually defined it that it's going to be from the material down for both sides. We can continue our work. So we've actually rectified that error now. So earlier, the first error that we encountered was the SOC, where we had to choose the material from the material. That's the particle material. So for porous electrode 2 and porous electrode 1, we went to the particle intercalation to choose that from the material. So now I think we can go ahead to compute our work. And I doubt we have any errors again. So after we get our results, we'll be plotting some graphs based on the electric potential versus time. As you can see, we have the electric potential boundary versus time. So I want us to plot some graphs as well. Oh, let's go to steady one. Let's go to time dependent and let's try and increase the solver again. Let's try and increase it to 600. Please, let's compute it. We have some plots here. Electric potential plot. We have the salt concentration and the boundary electrode potential expect to ground. Okay, so let's add a plot group, a 1D plot group. The label, let's type current. The plot settings. Want that to be current. A. Okay, so I want to add a global. I want to add a global. I want to place the expression model definitions. Go to the variables. Let's choose the drive cycle with the current. We have the current versus time. We have the plot of the current versus time. If you want to create another figure, want to create another figure. Want to create another figure to display the electrode potentials and cell voltage. So for comparison, we want to include the open circuit cell voltage at the load concentration gradient in the electrode particles accounted for. So we're going to add a 1D plot group. So let's type in here at the label cell and electrode voltages. Electrode voltages. I want that to be the voltage. So this figure will display the electrode potentials and the cell voltage. And add a global. Onto this expression. Variables, and we want to move to the battery cell voltage. Want to add another expression. Variables. Also added a positive electric potential. Want to add another. Definitions. Variables. negative electrode potential added. Definitions, variables, and the open and the electrode open circuit cell voltage, open circuit cell voltage at load. So we've added the battery cell voltage, the positive electrode potential, the negative electrode potential, open cell voltage. I'm going to enter this in the table. Plus Thus, the negative electrode voltage plus an additional 3.75 volts. So why are we doing this? Because we want to display the electrode potentials and cell voltage for comparison. We've included the open circuit voltage at the load, concentration gradients in the electrode particles so has been accounted for. So now that we are done with that, we want to, okay, we have our legends. I want us to make a manual, label our legends, cell voltage, because we have a lot of data we are plotting. We want to name each of them. Positive electrode potential, this is the negative electrode potential plus 2.75 volts. This is the open circuit cell voltage. Open circuit cell voltage at load. We can plot now. Okay. Okay, so now we have, now that we're done, I want us to create another figure. We want to, in order to investigate the cell and the electrodes are cycled within the allowed SOC windows, we have to represent it at the SOC loads. So that one will also require 1D plot group. So we type SOC. Y-axis label and SOC percentage. Yeah, the global like we did. You have to replace the expression, definitions, variables. And we select the SOC cell voltage at load. Add expression, definition, variables. Go to rather components, go to lithium ion battery particle intercalation, then average surface SOC. For porous electrode 1, then we add that for the porous electrode 2. Y-axis. Let's add some other. Let's input some other expressions. So this will be the SOC cell load. 600. That'll be 1, and this will be surface this will be same underscore surface. And we go ahead to locate the legends and manually put some label our legends. We have cell, we have the negative electrode, we have the positive electrode. SOC. Okay, the legends over here. Let's make it at the middle range. Okay. So now we have our plots, as you can see in here. So that brings us to the end of the segment. And if there are any questions, please kindly let me know in the comments below, and I'll do all to respond to all your comments. And thanks for watching, and I'll see you in the next video.